All right, so this is number 27. It says calculate and compare the energy of photons with a wavelength of 3 micrometers with a wavelength of 0.154 nanometers. And then use your figure 6.4 to identify the region of the EM spectrum to which each belongs. So the first thing that you want to be able to do is use the electromagnetic spectrum chart, and then you can get approximate values. So you can compare them, and then you could at least find the region that they're in. So the first one, 3 micrometers. So a micrometer, remember, micrometer is 10 to the negative 6th. So we would be at 3.3 times 10 to the negative 6th meters. And then nanometer remember, is 10 to the negative 9th. So 0.154 times 10 to the negative 9th meters. Those would be both of them in meters because we're given meters as units right here. And when we put them into our math equations, which I already have written up here, you're going to need them in meters anyway, because remember the speed of light is always in meters per second, and that matches with the Planck's constant as well. So let's put 3 times 10 to the negative 6th meters in here. That'd be right about here. It's a little bit larger than that, so it'd be a little bit this way. So it'd be right about here. And then if we drop that down and we want to find the energy in, it doesn't tell us, but let's just go to joules, and then we drop it down here. The units of joules are right here, so we'd be somewhere times 10 to the negative 19th. So somewhere approximately 10 to the negative 19th joules. And then for this one, 0.154 times 10 to the negative 9th. So now we're right here, 10 to the negative 9th, and 0.1 more than that, so we'd be a little bit this direction of it, getting a little bit bigger. Drop that down here, and we'd be somewhere, if I could draw my line a little bit straighter, 10 to the negative 15th. This would be 10 to the negative 16th, so we'd be maybe like 8 times 10 to the negative 15th, maybe 9 times 10 to the negative 15th. So, I'm sorry, like, this is 10 to the negative 16th, and so we'd be some number like 1 times 10 to the negative 16th, 2, 3, 4, 5, 6, 7, 8, 9, and then we'd get to 1 times 10 to the negative 15th. So this would probably be like 2 times 10 to the negative 16th joules or so. So this one would have much more energy than this one would, and then it wants you to look at where these are on the electromagnetic spectrum chart. And if we look just in terms of meters, 3 times 10 to the negative 6 meters, that would put us like right about here, probably in the infrared area. So this one would probably be in the IR area. And this one right here, 10 to the negative 9th, that would put us a little bit more in this area, right between the UV and the X-ray region, something like that, 10 to the negative 9th, probably more in the X-ray type of region right there. Okay, so mathematically, how do we do these? Well, first of all, keep that part to the side, and now let's go back to our two equations. First, we have equals C equals lambda nu. Solve it for nu. Nu is equal to C over lambda. Then, secondly, we have E equals H nu. And then, since we're given wavelengths for both of these, let's take nu and replace it with C over lambda. So if we replace it with C over lambda, now we have H times C over lambda, and that's our energy. So energy for the infrared one right here would be H times C over 3.3 times 10 to the negative 6th meters. Make sure it's in meters once again. And then energy for our X-ray one would be H times C over 0.154 times 10 to the negative 9th meters. Make sure you have it in meters once again. H and C, if you forgot, remember H is equal to 6.626 times 10 to the negative 34th joules times seconds. That's Planck's constant. And then C, remember, is 3.0 times 10 to the 8th meters per second, the speed of all electromagnetic radiation in a vacuum. So looking to put these into your calculator, go ahead and give it a try. You should end up with joules of about 6 times 10 to the negative 20th. So did we get close to 10 to the negative 19th? Yeah, we're 6 times 10 to the negative 20th. So, 7, 8, 9, 10 to the negative 20th is 10 to the negative 19th. So we got close. And then this one, when you plug that one in, you get 1.3 times 10 to the negative 15th. So it would be a little bit larger than this, but we got pretty close to the number of joules there as well. And we can see that this radiation has much more energy than this radiation, which makes sense because X-rays have much more penetrating power and are much more energetic than something over here that's in the infrared area.